Good morning, and we'll start this next section on In-situ Operando spectroscopy. And it's a great pleasure to introduce our keynote speaker, Dr. Jeff Miller, who's probably done all catalysis studies imaginable, maybe almost all anyway. With all his work, and collaborates very extensively with many people who work with beamline in Argonne. And I like this logo. If you can do it in the lab, you can put it on the beamline. So Jeff is really the leader in this area of doing in-situ Operando spectroscopy using X-ray absorption spectroscopy. It's a great pleasure to introduce Jeff.
Thank you, Israel. It's a great pleasure to be here, and thank you all for coming. I certainly appreciate the invitation to tell you about some of the things I do. I know many in the room use X-ray absorption spectroscopy for characterization of catalysts and all the different kinds of problems they have. And I really do think that one of the central themes of what I like to do is truly do it in the way that you would do it in the plant. That is, real temperatures, real gases, high pressure, liquid phase, even doing kinetics while you're running the catalyst. That's sort of the goal for this. And since there are lots of different problems and lots of different elements that you're interested in, we want to have the capabilities to do this for almost any sort of thing. So that's going to sort of be the theme of my talk today. I'm going to try to cover some of the basics and then get a little bit more advanced, and then sort of at the end I'll sort of tell you what I think is going to happen in the next few years. And I'm going to sort of do this in the form of two examples. I won't go into the full catalytic story. There have been talks at this meeting about some of this already, but I want to cover some sort of single-site catalysts. I'll use the Cobalt example to tell you about some of the basic principles, and then we'll talk about nanoparticles and nanorods, and we're working with another group. Okay? So I think for an audience like this, you know catalysis comes in all sorts of forms, and we have all sorts of problems. A variety of metals, a variety of process conditions. These are sort of catalytic applications. You certainly could look at problems like synthesis. How do I make the proper material? I'm also getting into electrocatalysis, and I admit that I know zero about electrocatalysis, but I do work with people who are experts, and I want to do the excess of that. So that's in a liquid environment. We're also doing homogeneous catalysts, which is not actually used very often in X-ray spectroscopy. We have cells which can do air-sensitive things the way the organometallic people do. So I won't talk much about those things, but if you have any interest in that, let me know. Okay, so here's the outline for my talk. I want to start out with a general introduction. I know many of you do X-ray spectroscopy. I don't want to spend a lot of time there, but for those who don't, I want to sort of give an overview of what you can learn. Then I would like to start with this sort of the traditional approach to X-ray spectroscopy. What do you learn? Oxidation states and structure. That's what many people do. Then we'll move into a little bit more difficult experiments. We're going to do time-dependent things. We're going to do multiple techniques. And we're going to watch the in-situ synthesis of cobalt nanorods. And I'm going to show you how once you really learn how to do the basics, it's not much more difficult to do complicated things. And then I hope there's enough time at the end I can tell you about what I think are some exciting developments at synchrotrons around the world and what we're going to try to do at the ATS. Okay, so X-ray absorption spectroscopy is based on the photoelectron effect. You pick an element in your sample, you have an electron, and you photoionize it. So it's an element-specific technique. We're going to talk about cobalt. Cobalt, we're going to ionize a 1s electron. So below the edge energy, we're going to have no absorption. When we get right to the edge energy, we're going to photoionize from a ground state to a bound excited state. That's the Zanes region, the X-ray absorption edge region. It has information about oxidation states, and then once you continue to give it more energy, you ionize the electron. It goes off with a wave that's related to its kinetic energy. It hits the electrons of the neighbors, it backscatters, and it sets up an interference pattern. And just like the rocks in a pond, you throw rocks in a pond and you get all these ripples, you get interferences, that the ripples are related to the geometry, how far apart they are, how big the atoms, and how many. So this excess region, the scattering region, has intrinsically in its structure, it's not easy to understand the structure from the ripples, but we're going to process the data and extract out the structural information. So that's the basic process. Here are the two types of spectra that you commonly see. This is the X-ray absorption near edge. There's a couple things that you worry about. In the 3Ds, we're going to look at little tiny feature that occurs before the edge. This is the pre-edge. The K edges for the 3Ds, the 1s to 2p is the dipole allowed transition. And because the only vacant p states are high-lying levels, it doesn't tell you much about the valence state. This little pre-edge is a spin-forbidden S to D transition. And this actually is very characteristic of the oxidation state. So this is actually how you determine the oxidation state, and I'll show you an example of that. The Zane's edge energy is the inflection point at the leading edge. Sometimes for the other elements, this is the part that you get the oxidation state from. And then, of course, there's the rest of it, which are electronic transitions. And I use this, most people use this as a fingerprint. And in mixtures, you can do linear combinations to determine the composition of the mixture that you have. This is the X-axis. Instead of showing you all the interference patterns, we do a Fourier transform, and we go from an energy space representation to a distance space. And now we're looking at the atoms further away from cobalt. So you excite the cobalt, and you look at it, and this is the first oxygen atoms around the cobalt ions. And then further away, beyond the oxygen, there's another cobalt. This is a cobalt oxide standard, and so this is a cobalt-oxygen-cobalt scattering path. And by using some theory or some experimental references, you can actually fit and extract out the structural information. We get the types of bonds, numbers of neighbors, bond distances. It's a basic local structure technique. You don't need long-range order. That's one of the powers of excess. I can do solutions. I can do amorphous materials. And most catalysts are pretty non-ordered, random sorts of structures, and so this is why XFs is so popular. The second reason XFs is popular, you're using high-energy X-rays. So you can do this under realistic conditions. You can go through the walls of reactors, through the windows, through the support. You see all the atoms in the sample. So it's a bulk technique. One of the limitations is, in order to see the chemistry, you have to have a high fraction of surface atoms. So I'm always interested in really, really small nanoparticles or single sites so that every atom is the catalytic species. Then you begin to see some real information. We can build cells. We have cells that will go to 900 degrees, others that will go to high pressure, 50, even higher pressures. We can run liquid phase. We can do plug flow kinetics. We now have things to run solutions. So if you have a problem, I think it's reasonably possible to solve whatever your catalytic system is and do it under the realistic conditions. And I'll show you some examples. These are our standard cells, very simple thing. We've been using these for a long time. It's just a quartz tube. We have the cage-on fittings. We weld a little fitting and we put a shut-off valve here. We blow gases in and out. We stick it in a furnace. We can stick that right on the beam line. And you can put this under all sorts of gas conditions. You can either run it in the lab and then put it on the beam line, or run it at temperature on the beam line, and you can sort of see the state of your catalyst. Now, the synchrotrons have gotten so good. It used to be you'd go out and you'd spend 8 hours and you'd collect data on one sample. Now that same spectra can be done in 2 minutes, so you can do lots of things. The rate limiting step now is not data collection, it's pre-treatment. So this actually, I don't know if you can see it, but there are 6 samples. We treat 6 samples at a time. We do them all, if they can all be done under the same conditions, and then we have a movable sample stage, and we just run the 6 samples, and then we load up. While those are being run, we treat others in the lab and continuously move the sample through. We will actually run 100 samples per day because the productivity of the number of photons. We have a fluorescence furnace. If you have low concentrations, you have a support like Syria, which absorbs all the photons. You do it in fluorescence. Again, we can do this on the beam line. We put a fluorescence detector on this big face, and we look at the fluorescence. This is sort of the standard thing that people have been able to do for a long time, and we use this a lot. Once you can do this, you say, look, I like to do kinetics and be sure that my catalyst is really operating, and I'm not just treating it in some artificial conditions. So in conjunction with Fabio Ribeiro and his group, we've built a plug flow reactor. It's a conventional pilot plant design, a lab plant design. We have flow controllers. This is set up for selective catalytic reduction. There's a water saturator, but we also use this for other reactors. We have liquid pumps, high pressure, back pressure regulators, gas liquid separators. You can do a fully operational pilot unit put it on the beam line, and what makes it possible to do the XFs is instead of the stainless steel tube, which you might use in the lab, we have this nice, beautiful glassy carbon transparent to the X-rays. So we load the sample in here, and the X-rays go right through the wall. We treat our sample, we get the kinetics off. This is, for the SDR, he's got this nice FTIR detector. We can put a QC on it and do any kind of thing you can do in the lab. All right? This is the aluminum block. This is a cartridge heater, and this is the back face. You put another face over the front. There's a little slit in the walls, and you can even look at the top and the bottom of the bed to see if there are any differences in the catalyst structure. And once in a while we do that. Okay. Here's actually what it looks like if you want to go do an operando spectrum. This again is set up for SCR. Here's the FTIR detector. The little cells over here, the beam lines over here. We've got 6 different gases going in. We've got temperature controllers. You can see it's kind of involved to set this up. The Purdue guys come down, and I think it takes them, a full 8 to 10 hours to set this up, another few hours to pre-treat catalysts. So it's not something you just walk in and do in 5 minutes, but if you really want to do this, it's really, really, really nice. And I would, if you're interested in SCR, Shane's going to talk about this in the next talk right after mine. He'll tell you about what he did with all this equipment. And also, Fabio has a keynote lecture this afternoon in a different session. And if you're interested in SCR, I recommend that you go to that. Okay, so let me go through a few examples. We're working with some single-site catalysts on silica, but how do we know that? We've put some transition metals on silica, and we're using them for propane dehydrogenation at high temperature. And so we have a catalyst. This is an example of one of the good catalysts that we make. And we can run the conversion. We change the temperature, run the conversions. Just to show you, this can be run at high conversion. We make very little methane in other products. We make mostly propylene. Selectivities are often close to perfect, 95 to 100%. These things last. They don't deactivate. They don't coke up. They last until we get tired of running them. So the question is, what is the catalytic site? We also make catalysts that aren't too terribly good if we make it a different way or make it poorly. And so how do we use XFs? We use XFs to say, how do we optimize the structure? Why is a good one good and a bad one bad? How do we change the synthesis to always get the good catalyst? And then, of course, what's the active state? Is it metallic? Is it an oxidized sample? Is it going through a redox cycle? What are the coordination geometries? And, of course, we don't just do XFs. We have lots of other things. We have an outstanding capabilities about Raman Spectroscopy and DFT. And we use all of those things. I'm only going to go through some of the XFs part of this. Adam Hawk gave a talk on Monday about all the catalysis of these things. So I do want to go through some of the things, but I'm going to emphasize mostly the XFs in this talk. Let me acknowledge the collaborators here. Bill Hugh is a student from IIT who works for Adam Hawk. Neil Schweitzer was a postdoc of mine who's now up at Northwestern in the catalyst testing lab that they now have. Ujjal Das just gave a talk this morning in another session about the density functional theory work that he's been doing. Hawk Sun Kim and Peter Stair are the Raman and infrared spectroscopy experts that we have on this project. Jeff Greeley, Ujjal works for Jeff Greeley and Larry Curtis, and Jeff has just moved to Purdue. It is going to be in the chemical engineering department. They're doing theory. Okay, so how do we make the catalyst? We make the catalyst following the John Rigobuto method of synthesis. We absorb ions onto the support under controlled pH conditions. So the basic principles are you have an oxide support that's sort of represented in yellow, and it has OH groups, and those OH groups have a characteristic pH in solution where they're neutrally charged. That's the point of zero charge. If you acidify the solution relative to that pH, you protonate the surface, and if you basify it, you create oxide sites and a negative charge. We're going to use silica. The point of zero charge is 4. We're going to use base to deprotonate it, so we're going to have a negatively charged silica surface. With a negatively charged silica surface, we can absorb in a monolayer cation complexes. And so we're going to use the cobalt hexamine. This is a commercial sample from, we get this out of Aldrich. And we simply absorb the cobalt-3 amine onto the surface. We dry it, we heat it, we pre-treat it, and we get our active catalyst. Okay, so what can XFs tell us about the catalyst preparation? Well, this is just sort of qualitatively what we see. If we absorb the Cobalt-3 complex onto the support, we have this black spectra. And just by drying even at 125 degrees, you can see there's a change. There's a shift in the edge position, shift in the pre-edge position, and a change in the shape of the zanes. We heat it to higher temperature, whether it's 300 or 500. There's an additional change. There's no change in the edge position or the pre-edge, but there are subtle changes in the shape of the zanes. Okay? In the excess region, the starting complex has, it's known to have 6 amines, and so it has a position here. In the Fourier transform, the size is proportional to the numbers of bonds, and this imaginary part is proportional to the bond distance, just qualitatively. And you can see when we go to 125 degree drying, the peak is smaller. That means we've lost ligands. There's also been a small change in the bond distance. And we're going to fit that, and I'm going to show you what we learn about the synthesis by just following basic kind of excess. So, how do we determine the oxidation states? I said before, the pre-edge is a S to D forbidden transition. That's why it's small, but it does correlate with the oxidation state. So here's a bunch of reference compounds, known structure and oxidation state, and we measure the edge of the pre-edge energy, and we're talking about measuring 77,000 electron volts, and over this range we have a 1 electron volt difference. And you might say, that's not very much. Can you really reliably and reproducibly measure that? And the answer is, if you calibrate it properly with coils, which is the way everybody does it, you can in fact reproducibly measure that edge energy to about 0.1 eV out of 77,000. It's pretty good. And using that, then you can run an unknown sample, look on the scale, and say, what's the oxidation state? Okay, that's what we do. So here's the fits for some of those synthesis steps. We start with a precursor. It's a Cobalt-3 compound with 6 bonds, and this is the XRD bond distance. We use that as the reference for the excess. When we dry it, we're still Cobalt-3. We still have 6 bonds, and we're still at the same bond distance. So absorbing onto the support and drying just at room temperature doesn't change anything. That makes sense. When we heat it to 125, we see a change in the edge and the pre-edge. It goes to a +2. That's exactly the energy the +2 references. We now go from 6 to 4 bonds. We've lost 2 ligands, and we've changed the bond distance. It's gotten a little bit longer. Okay, well at 125 degrees, you've probably just lost 2 amine ligands. Okay, probably not done anything more than that. Now at 300 degrees, we're still at the same edge energy and pre-edge. There were some changes in the shape, but the oxidation state really doesn't change. And also the coordination geometry. There's still 4 bonds, but there is in fact a change in the bond distance. Now, you can't tell an oxygen from a nitrogen. XF's the scattering technique is proportional to electrons. Nitrogen and oxygen differ by an electron, so you can't really tell the atom type. But because we treated this at 300 degrees, and you'll see the 500 degrees is the same answer, and the change in bond distance, I would assign this to an oxygen ligand. We've lost the amines, and we've now formed oxygen bonds to the support. Okay, and you get this exactly the same answer at 550 degrees in air. Well, that sort of tells us what our catalysis is. Cobalt-2, 4 bonds to the surface of silica. But what we really care about, what does it do under catalytic reactions? So we're doing propane dehydrogenation. At 550 degrees, we still have +2. We still have 4 bonds at 1.97. We didn't change a thing. It doesn't show any evidence of reduced cobalt. It doesn't show any evidence of Cobalt-1. No oxidation. We didn't do an oxidative addition. It's exactly the same structure at 550 degrees, 650 degrees. And we can do the reaction at 550, which in fact we've done. We still no changes. We can do it in helium. We can do it in air. We can do it in hydrogen. This cobalt species doesn't change under reaction conditions. Although it doesn't change oxidation state, it still does catalytic chemistry. It does hydrogenation and it does dehydrogenation, but it's not a classical metallic center, and it's not a classical homogeneous oxidative addition mechanism. So this is kind of why we're interested in these things. Okay, we also do the same thing with zinc. Absorb it onto the support in exactly the same way. There are stable zinc amines in basic solution. This dotted line is zinc foil. The red dotted line is zinc oxide, and you can see our catalyst has the same edge energy as zinc oxide. It's zinc 2, but it has a different shape. The x-axis is shown down here. When we prepare the catalyst, we have this blue curve, and there are 4 bonds, 1.93 angstroms. And as we start to heat it above 200 degrees, and it's the same whether we're in hydrogen, helium, or oxygen. It's not a reduction, it's a thermal transition. We start to lose a little bit, a very small amount. And you look at that and you do these experiments, you have to do this several times to believe that small change is real. But as we keep going up in temperature, you lose more and more and more of this oxygen, one of these oxygen ligands. By the time we get to 550, where we do the propane, we've lost a full ligand. We now only have 3 bonds around zinc, still at about the same bond distance. And this is the point at which we start to lose this oxygen ligand going from 4 to below 4. This is exactly the point where we start to generate catalytic activity. We're getting coordinatively unsaturated zinc. In fact, we've done the infrared. These are Lewis acid sites. These Lewis acid sites are doing carbon-hydrogen and hydrogen activation. All right, so this is a talk about X-ray spectroscopy, but I do want to sort of complete the story here. We've done, Peter Stair and Haksung Kim have done the Raman Spectroscopy. This is the Raman Spectroscopy system silica support we use. These studies have been done previously, and we see the same bands. Here are the Raman bands that we see. I've only shown a portion of the spectrum. These are the density functional theory calculations that Ujjal's done. These agree with the assignments. These agree with what's in the literature. And you'll notice the reason I show this part of the spectrum, this peak here corresponds to this 3-membered siloxane ring, 3 silicons, 3 oxygens. And when we absorb metal ions onto the support, we lose that band. We think this is the site at which these tetrahedral coordinated cations are going into. It opens up the ring and creates a 4-membered ring, one of which is now the metal ion, whether it's cobalt or whether it's zinc. And in the case of zinc, at high temperature, we actually lose the coordination, whereas in cobalt, we didn't lose the coordination. All right, so that's... and we've also looked at the density functional theory, which all gave a talk this morning. We've looked at a variety of reaction mechanisms from free radical to other kinds of things. This is the lowest free energy path, and this is what we think is the chemistry that's going on. We have a coordinatively unsaturated site. Propane comes in. There is, at the Lewis acid site, there is a heterolytic cleavage of the carbon-hydrogen bond. That leads to a proton, H+, on the oxygen atom and a C-. So the 2 electrons stay with the carbon, and we get a proton transfer to the support. It goes through the cycle. We get a beta hydrogen elimination, forming a zinc hydride and a proton. This then eliminates hydrogen and completes the cycle, and hydrogenation, which this catalyst also does, goes just in the opposite pathway. So we think this is a Lewis acid site doing heterolytic hydrogen and CH cleavage, which we think is a little different than many hydrogenation mechanisms. We're in the process of trying to confirm this by spectroscopy. We think we've identified this OH here, by Raman, but we're just really beginning that stuff. All right, so that's standard XFs. That's structure, that's oxidation states, that's under chemical reactions. So now what I'd like to sort of change the topic and show you that you can start to do these fast. The modern synchrotrons have lots of photons. Spectra can be taken. We're going to take some of these in a minute, but you can take a high-quality XF spectra in this 10 to 20 seconds. You can get the whole Zanes and the whole XFs and do a complete fit, so you can do time-dependent studies. So you can actually start to look at kinetics of processes. And we're going to look at the formation of cobalt nanoparticles and nanorods. This work comes from the group of Bruno Chaudret and Toulouse. Bruno has a team. Katerina is a staff scientist. 2 PhD students, Nikos and Tomas. This is the topic of their PhD exam, making these nanorods. These are not really being used for catalysts. They're actually interested in these as magnetic materials, and actually some, I think some cancer therapies actually. But I have actually used this technique to make supported metal nanoparticles that you can't make cobalt and iron and these kinds of things with traditional aqueous systems. So this is a really nice way to make supported metal nanoparticles of the 3D elements. The principle is you start with a nice reactive organometallic cobalt-2 system. This hexamethyl disilane sort of ligand is very unstable, and you heat this up, it will reduce the cobalt nanoparticles. But they also throw in lauric acid and hexadecylamine. And depending on the stoichiometry of these two ligands, they get different answers. So in one case, when they add this ratio, they get rods. And it's not only making cobalt rods, but the rods stack together in groups of rods. In other conditions, they actually get nanoparticles, 3 nanometer nanoparticles, which is pretty impressive for cobalt. 100% fully reduced 3 nanometer cobalt is really hard to do by traditional synthesis routes. And then there's another synthesis that they throw things together, nothing happens. No matter what you do, it doesn't reduce. So they were really interested in why all these different outcomes with this different stoichiometry. This is done at 150 degrees with 3 atmospheres of hydrogen in a liquid phase with very dilute concentrations. So this is a sort of a challenge for XS. Just to show you some of the materials, they have these are, you can sort of see the rods, and they tend to stack like this in parallel planes. And they also get some twinning under some conditions. And then when they do other things, they get nanoparticles. The length of the rods is somewhere around 17 nanometers, and the diameter of the rods is about 3 to 4 nanometers, and the distance between the rods is about 14 nanometers. And those are some of the things we're going to try to see as we go along. So in order to do this in an XFS experiment, you need an air-sensitive cell, you need a glove box to set this all up. So we've been working on some homogeneous organometallic cells. And so this was our low-temperature version. This body is cavities, and we have hooked this up to a cold bath, and we send cooling fluid. And this will go minus 40 to 90 degrees, and so we can thermally unstable materials. This is PEEK. You just buy a rod of PEEK, and you have a machine shop cut it out, and we cut different dimensions depending on the path length that we need. We have a typical sort of swage lock type fitting, and we can load it and run the cell. We have caps where we can inject the organometallic reagents, or we can even flow gases through here at high pressure. We put back pressure regulator and we can flow gas. So we have this nice capability, but these reactions are done at 150 degrees. PEEK's not stable at 150. The cell's not really capable. So I was talking with Fabio about this, and he was interested in some nanoparticle stuff, so he said, I think I can build you a high-temperature cell. So we went down, and this is the high-temperature version. It's got electric cartridge heaters in it. We found a high-temperature polymer material that goes up to 250 degrees and is stable. And then we have the top, which we pressurize with high-pressure hydrogen. So that's the cell. And we're going to also, we want to watch the reduction in nanoparticles and things and do the kinetics of that, but we also want to see the morphology things. When do we form rods? When do they assemble? Are they assembled under reaction conditions, or does it form on cooling? So we wanted to also do, at the same time, small angle scattering. So we built this little small angle scattering tube, and this is on a table. So the beam comes through here, goes through the sample, now it's doing small angle scattering. We do that, expectorate, and it takes about 10 seconds. The table moves the detector for the excess back in position, and now we do the excess. We do a couple XFs experiments, then we move back to the sex. We do this this reaction takes, initially they thought it took 24 hours. It turns out it's faster than that, but a typical experiment might be 6 hours. So we're taking spectra on like this for 6 hours. Okay, and Jeremy was instrumental in building the equipment, and Elizabeth, this is Katerina from Toulouse, these are her nanoparticles. She came, I would suggest if you want to do any of these in-situ things, you got to come into the lab and use the equipment, because this is not the thing she makes nanoparticles. She spent 3 weeks in the lab learning to make nanoparticles in our cells, so we'd be sure when we got to the beamline it really worked. I think that's also the same thing we recommend about the Operando plug flow reactor. You've got to run it in the lab before you actually bring it all to the beamline. It's a big setup, and you really don't have time at the beamline to learn how to do the experiments. So this is the group that really made these experiments possible. Here's sort of this range region for what happens. We start with the red curve, which is the very bottom curve. You can see the little Cobalt 2 free edge feature, and it has a big edge. And then as we go along in time, we stick it in the cell, it starts to heat up, it's under hydrogen. Then this region starts to get bigger and this region starts to get smaller. And you can actually fit the spectra with the starting Cobalt-2 and the final cobalt metal precursors. And so you just do a linear combination. You know when you've got a time on when each of these spectra were taken, and so now you have the ability to know the composition as a function of time, and you can actually determine kinetics. Okay. All right, so here's the excess. This is at the end. This is the cobalt phase. You can see the blue is cobalt foil. This is the rods. You can see the imaginary part has the same bond distance. You can see the coordination is smaller. We make 3 nanometer diameter cobalt rods. That's what the excess tells us. Here's the kinetics. It turns out that these things reduce in about 30 minutes, but they turn out to be 2 kinetic steps. There's an initial step, and then at some later time, they get a different rate. And it turns out that when we look at this thing, there's actually 2 types of cobalt. There's the cobalt precursor that you start with, and if you have something like that, it decomposes almost instantly to cobalt nanoparticles. That's when you get the cobalt nanoparticles. There's another form of cobalt, when you throw the lauric acid in there, it doesn't reduce at all. When you put the right combination, you have a fast-reducing cobalt and a slow-reducing cobalt. The cobalt nanoparticles act as the catalyst in the presence of hydrogen and catalyze reduction of the slowly reducing stuff, and you grow rods. And the rods are so that's the 2 kinetic processes. You find the fast decomposition of nanoparticles, and then you find a different rate for the rod formation. So that's what excess tell you. But that's, in addition to the size and the bond distances and the amount that's reduced, that's all that excess can tell you. But they want to know so much more, and that really comes from Sachs. So Sachs is this is an excess person doing Sachs. And for those of you who do Sachs, you say, oh, how bad is this? We didn't realize the polymer had all sorts of signal. There's big background stuff, and it interferes badly. The Sachs guys straightened this out, and we do much better now. But this is actually a peak that's due to the interspatial spacing between the rods. This is about 14 nanometers, which exactly matches the TEM. This polymer interferes with the rest of the spectra, but if you look at it hard enough, you can sort of see things changing. At this point, we decided we better get some experts involved, and so we went to the Sachs experiment. This is the Sachs beamline at the APS. So instead of a little tube, they have a detector that runs back and forth. They get a much wider Q range. They have software to do background subtraction, and they can do a much better job of doing Sachs. So here's the same experiment done by a Sachs guy on the Sachs beamline. You see the same peak. This is the rod, the interspatial spacing of the rod, and now you do see there was a feature out here where we had all this polymer overlapping, and you can see it changing as a function of time. And this is actually the rods growing longer and longer and longer with time. And in fact, if you fit that, you can probably determine the growth rates. Okay? So Sachs adds an awful lot to this, and what we do see is this is actually at 150 growing in time. So these are all in situ at reaction conditions. This doesn't happen on cooling. This happens under reaction conditions. So let me finish in the last couple minutes. I want to sort of give you sort of a flavor of what's going to be possible in the next few years. So there's some elegant things. So this is sort of the X-ray translucent. You ionize your sample, and the core electron goes into a vacant site in the d orbitals. That's at least at the L edge. That gives you the information about the number of unfilled states in your sample, and that's important. But what you'd really like to know also is what's the energy of the filled states, because adsorbates bond to the electron density of the metal. So you really like to do something. So there is a way to determine that. It's called resonant inelastic scattering. So when you look at the photons that are emitted when this thing decays back to the ground state. The way this is done in most synchrotrons is that you go to a standard fluorescence experiment, and you get a whole bunch of different frequency X-rays that come on. But you really only want to select one that's characteristic of this frequency here. So you, at a certain position away from your sample, at a certain angle, you put a whole series of crystals which are specially machined, and you refract those things to a certain angle, and you can put your detector out here. It's a very difficult, complicated experiment. But when you do that, you get the energy difference between the filled and the unfilled states. It's called resonant inelastic scattering. The problem is this is rather expensive and difficult to do, and for every single experiment, every single edge, you need a different spectrometer. So we have a different approach. Jeremy Croft and Bruce Ravel are working on a technique where you take a silicon crystal, a thin silicon crystal, and you bend it. Now you have a whole bunch of different angles to the silicon crystal. You look at your fluorescence that comes here, and each energy comes off at a different angle, and then you just move your detector around to pick up what you want. And the beauty of this is Bruce and Jeremy did gold one day, platinum the next day, in the high-resolution Zanes mode, and then they did resonant inelastic the third day. You can do many elements and many different kinds of experiments with a single spectrometer. So this is the prototype. This is sort of put together with spare parts, and it's not very pretty. Jeremy's in the process of building a more permanent and a more elegant spectrometer. You probably can't see it. This is this little crystal. Here's sort of a blow-up. It's on an aluminum, a bent aluminum thing. You just bend aluminum crystal. It's also got some slits to filter out the energies. And here's the enhancement and signal to noise. This is the Zanes. The blue, these are both platinum foil. This is the intensity of the Zanes if you just take one of the fluorescence energy. Okay? You get far better resolution. And Bruce actually had some gold things that had Zanes that looked exactly the same in the standard mode, but when you went to high resolution mode, they looked different enough that you could sort of do linear combinations and figure out composition. I think this is the future of doing Zanes and synchrotrons. Now you have to have a spectrometer. Here's the actual resonant inelastic scattering. This is the way you represent. This is the energy loss. This is the difference between the filled and the unfilled states at a given energy. This is for platinum foil. We made this experiment work. The platinum foils are 100% platinum, and catalysts are 1% platinum, right? 1% platinum. We don't have enough signal yet. The good news is he's going to build 4 detectors. The APS and other synchrotrons are upgrading the number of photons. I think in 2 or 3 years this is going to become a sort of a standard experiment, and you're going to be able to determine the energy of both the filled and the unfilled states, which is going to make interesting comparisons to density functional theory, and I think that's where we're thinking we're going to be doing experiments in the next few years. But let me just show you, we have done one thing with Randall Meyer's group at UIC. Randall's interested in selective hydrogenation of acrolein. This is the pathway that you want to go. You want to saturate the double bonded oxygen. And silver is the best catalyst. If you do palladium, palladium's a lot more active, but it's not selective. But when you get to 0.01% palladium, you get both an enhancement of activity and selectivity. The problem is, what's the palladium doing? At 0.01%, you can't detect it by XRD, TEM, chemisorption, infrared. It's just too small. So we looked at this by this high energy resolution. We filtered out all the background fluorescence problems, and we end up being able to detect the palladium. And the palladium coordination number exactly matches that of the silver. The bond distance tells us that palladium is surrounded by silver. It's isolated, both in the bulk and on the surface. And so this technique allows you to do things that you really can't do in the standard mode. And I think this is why we're so excited about these capabilities. So let me finish. I've talked to you about X-ray absorption. I think it's appropriate for all sorts of problems. Synthesis, catalyst sites, poisoning, aging. I actually looked at this a lot in industry when I did that to solve practical problems. This is not just an academic exercise. So with that, I'll close, and hopefully I'll have a little time for questions. Thank you.
So this paper is now open for questions. John, you boot up?
John Bigelow from South Carolina. Jeff, I'm trying to rectify your work with what Bruce was telling us yesterday about the support as ligand. And I don't recall seeing silica or whatever your support happens to be in the outer coordination shell of some of the things we've seen. Does that mean that there's a critical size, or maybe we can consider the supported ligand only for the very smallest clusters or atoms, or what do you think about supported ligand, and if so, should you be able to see it with XM?
So I do believe that the support is a ligand. We see a very tiny higher shell. It looks exactly like the higher shell of iron and ZSM5. That is, it's iron, oxygen, silicon. Very small. That's the ligand, the silicate. If you change to titania, cerium, and other things, you change the bond strength. You do, in fact, have ligand control using oxides. Now, how much can you do with oxides? I don't know. Bruce was actually using real ligands in some of these things. No, I agree. What we change more than the ligand type from the support is the coordination geometry. Cobalt goes tetrahedral, nickel actually goes octahedral. And a lot of the other bigger ions tend to have different coordination. But these all tend to be coordinatedly unsaturated. I think that's why these turn out to be interesting catalysts.
Thank you.
So we're out of time. If everyone wants to talk to Jeff, I'm sure he'll talk to you in private. So thank you very much.
The next speaker in the session is representing a collaboration